Hello everyone, this is Abhishek Mathur. I'm your physics faculty for JEE Mains at Altedemy, and in today's lecture we're going to see the basic things which we need to know so that we can proceed further into the chapter of semiconductors. So this is an introduction video. We will be learning the basics and mostly the introduction part, all right, and then you will get all the notes in the PDF form and you can go through the notes, right? So the first thing which we have to understand is the concept of energy bands. The concept of energy bands. In the chemistry, you must have learned the energy levels 1s2, 2s2, 2p6, 3s2, 3p6. See, when we talk about one particular atom, the electrons are having a particular value of energy. All right, electrons have electrons electrons have electrons have fixed value of fixed value of energy fixed value of energy, right? Electrons have beta fixed value of energy when we are talking about one single atom, but we know that one single atom does not exist. In majority of the cases there is a collection of atoms. Most of we have If we have a particular piece of a metal or a particular element, that particular element will not have only one atom, there will be so many atoms, all right? So when so many atoms come close to each other and they interact with each other, their energy levels interact, and we are talking mostly about the outermost energy level. The outermost energy level occupied by an electron. So when that energy level which is occupied by the electron interacts with another electron of the same energy level, there is energy interaction, and due to this energy interaction, if we had a particular value of energy, now this particular value becomes a band, because some electron while interacting will gain energy and some will lose energy. So instead of a fixed value, instead of a fixed value, what we will get is a band. This was a fixed value and this is a band. This is a band of energy, all right? So these are energy bands. This is how energy bands are formed, all right? And then we have valence band. The band which is partially or fully filled. The band which is partially or fully filled is your conduction band, and the band which is your fully filled, outermost outermost fully filled fully filled band. Outermost fully filled band is known as valence band. What is valence band, beta? Valence band is outermost fully filled band. This is your valence band, all right? And these are the properties: have bonded electrons, no flow of current due to such electron, always fulfilled by electron, because this particular band is always fully filled, all right? And then we have conduction band. See, a conduction band is formed by the interaction of electrons in the outermost region, all right? Those electrons which occupy the outermost uh, you know energy level, when they interact they form a conduction band, and it may be partially or fully filled. Partially partially or fully filled, can be partially or fully filled, all right? Range of energies possessed by a free electron is known as conduction band. It has conducting electrons. Current flows due to such electrons. If conduction band is fully empty, then current conduction is not possible. All right, because what happens is, if this is a conduction band, then if it is partially full, if it is partially filled, it means that electron here can jump in the same band. This electron can jump in the same band to here, to a higher value of energy. When it will gain some energy, it can go to a higher place, all right? So for the conduction of current, mostly conduction band is responsible, right? Then what is energy gap? What is energy gap? The energy gap is something which is really very important. If this is my conduction band, if this is my conduction band, and this is my conduction band, and this is my valence band, this is my valence band, this is valence band beta, this is conduction band. So the gap between valence band and conduction band is your energy gap. And this energy gap is something which determines whether a material is a conductor or an insulator or a semiconductor. All right, so this is the energy gap. Great. Then we have the concepts of hole. We have the concepts of hole. See, in valence band, in valence band, in valence band, in valence band beta, when an electron leaves its place, when an electron leaves its place, a vacancy is created. A vacancy is created, and that vacancy is treated as a positive charge, and that vacancy is treated as a positive charge beta. Okay, vacancy is treated as a positive charge. And to fill this vacancy, an electron from neighborhood will come and occupy its place. If this will happen, then a hole will be created, at the place of electron. So we treat hole as a positive charge. Hole is treated hole is treated as a positive charge, charge. Right. So what is a hole? It is the deficiency of electron in valence band. Its mobility is less than electron. It acts as a positive charge. Alright, these are the points which we have discussed. And then effect of impurity in semiconductors. See, the conductivity of semiconductors is much higher than insulators, but it is still very less compared to conductors. So what we do is, this is something which you might have already studied in chemistry, the first chapter of chemistry of 12th standard, solid state. Doping. What is doping, beta? Doping is the addition of impurity in a pure semiconductor. All right. So pure semiconductor is also known as intrinsic semiconductor. Effect of impurity in semiconductors. Doping. What is doping? Doping is addition of impurity. And what impurity? Desirable impurity. What kind of impurity you want to add? It is your desirable impurity. And from here we get two types of semiconductor, either p-type or n-type semiconductor. Either we will get p-type semiconductor or we will get n-type semiconductor. Clear, beta? All right. So what we do is, we use aluminium, phosphorus, these kind of elements in a pure semiconductor. What is a pure semiconductor? Your pure semiconductor is going to be silicon or germanium. All right. Great. So this is a type of flow chart. Semiconductor are of two types. One is intrinsic. Intrinsic means pure, and then extrinsic. Extrinsic means doped. Those semiconductors which are created by doping, when you have added some impurity. And then in pure semiconductor we have germanium and silicon. In n-type we have phosphorus, arsenic, etc. All right. And in p-type we have trivalent impurity, and in n-type we have pentavalent impurity. The pentavalent impurity is this, and the trivalent is gallium, aluminium, indium, etc. So when we talk about n-type semiconductor, the concentration of electrons is more than holes, and in case of p-type impurity, the concentration of hole is much greater than concentration of electron. All right, this is my p-type. Great. And then this is the theory for n-type semiconductor. How n-type semiconductor will be formed. To form n-type semiconductor, what we have to do is, we have to dope a pure semiconductor. We have to dope a pure semiconductor, silicon or germanium, with a pentavalent impurity, and these are the pentavalent impurities. All right, great. And the majority charge carriers are free electrons, and minority charge carriers and holes are the minority charge carriers in case of n-type semiconductor. All right, and then we have p-type semiconductor. In case of p-type semiconductor, what we do is we dope silicon or germanium with a trivalent impurity like aluminium, gallium, barium, like these. All right, so in this what happens is, because aluminium has 3 electrons and silicon has 4 bonds. So when we will use aluminium beta, aluminium will give 3 electrons, so it means that only 3 bonds can be broken. This electron will take place here, and third electron the third electron is taking place. I'm sorry, I have drawn a few things wrong, let me correct them. So this electron will take this place, this will take this place. Oh, this electron will take this place and this will take this place. So this is a hole. So when we are removing one silicon atom and replacing it with an aluminium atom, so aluminium will bring with itself 3 valence electrons, but when the silicon was present there, silicon had 4 valence electrons. So when compared to silicon, there is a deficiency of 1 electron. That's why one hole is created. By doing this, adding by adding one impurity in 10 raised to power 6 atom, we can improve the conductivity drastically, right? So in p-type semiconductor beta, free electrons are minority charge carriers and holes are majority charge carriers. Great. Let's talk about PN junction. What is PN junction? See, PN junction is something which is really very important. PN junction is really very important. Please pay attention, beta. What is PN junction? To form PN junction, we we dope we dope pure semiconductor. We dope pure semiconductor, pure semiconductor with 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 trivalent trivalent or or pentavalent or pentavalent impurity, right? So what we are doing is, if I'm having a semiconductor, pure semiconductor, what I will do is I will dope this with either trivalent impurity or pentavalent impurity, and after that, and after doing this, I have to dope it with the other kind of impurity. For example, if I have used trivalent impurity first, if I have used trivalent impurity first, then what will happen, beta? If I have used a trivalent impurity, it will become p-type, it will become p-type semiconductor. Now since it is a p-type semiconductor and I want PN junction, what do I want? I want PN junction to be formed. So I will dope one side, this is your first step. In second step, dope dope with dope with dope with pentavalent 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 on another side. So what we are doing is, first we are making the semiconductor as p type or n type, and then if semiconductor is p type, say for example, then I want the PN junction to be formed. So what I will do is I will dope this particular side, with pentavalent, with pentavalent impurity, in high concentration, because see the whole pure semiconductor is converted into p type. So what I will do is I will simply dope the one side of the p type, so that one side will have more number of electrons and one side will have more number of holes. So what happens is, if this is my p type semiconductor, if this is my p type semiconductor, I have, positive charge carriers here. I have positive charge carriers here, and the other side is doped, and the other side is doped, and the other side is doped with n type. So now this can't remain like this, because at one side the concentration of electrons is more, at the other side the concentration of hole is more. So due to the concentration difference, the diffusion process will start. Due to difference in concentration, diffusion process will start, and what we will get finally is, this. We will get something like this. Please pay attention, everyone. We will have positive charge here, we will have negative charge here, we will have negative charge here. But due to diffusion beta, but due to diffusion, there will be positive charge, negative charge, positive charge, negative charge. Sorry, this will be the final arrangement. This will be the final arrangement. All right, great. This particular region beta, where the diffusion has taken place, is known as depletion layer. This is your depletion layer. This is your depletion layer, right? This was the introduction of PN junction, right? Now let's talk about forward bias. What is forward bias beta? When we talk about forward bias, the p side, as you can see, the p side is connected to positive side, and n side is connected to negative side. This arrangement of PN junction is known as forward bias beta. This is forward bias, right? And if the p side is connected to negative terminal, as you can see here, the p side is connected to negative terminal and n is connected to positive terminal, this is known as reverse bias of the PN junction. All right, great. Now let's talk about LED. What is LED? LED is a device. LED is a device which you must have seen LEDs, right? In your headlights of car or at Diwali. Or what is LED? LED is forward biased PN junction. What is LED? This is a forward biased PN junction, and it emits spontaneous light. That's why we can see the light coming out of the LEDs. All right. So there are certain advantages of LEDs, and these are low operational voltage, less power, fast action, light emitted is nearly monochromatic, they have a long life, right? And then we have photodiode. What is photodiode? Photodiode is also a PN junction, but unlike LED, it is reversed bias. It is reversed bias. All right. So what happens is electron hole pairs are created at the junction, due to which additional charge begins to flow across the junction. All right, and this is due to minority charge carrier. All right, so this was our photodiode. Let's talk about xenodiode. See, xenodiode is something which is really very important, and there has been a lot of questions asked. All right, a lot of questions, a lot of questions has been asked on xenodiode, right? So what is xenodiode? Xenodiode is basically PN junction which is reverse biased, When it is reverse biased, what happens is the potential barrier or the depletion layer breaks. due to which there is a very high surge in the current, and the potential difference remains constant and the current increases drastically. So basically what's happening is the current is increasing, but there is no as such increase, there is no as such increase in the voltage, in the voltage. So if I try to draw the diagram for reverse bias, it is something like this. This is known as breakdown voltage, this is known as breakdown voltage, breakdown voltage. And at the y-axis I'm taking the current, and at this I'm taking the voltage. So Zener diode is operated at reverse bias. It is operated at, see, this is positive side of V, this is negative side of V. I hope you can see this. So Zener diode is something which is operated in reverse bias, and at a particular voltage which is known as breakdown voltage, the voltage does not increase further but the current increases. Alright, so that's why it is used as a voltage regulator, and in the next class we will be doing a lot of questions which are asked on Zener diode. Alright, now what is a transistor? See, in PN junction we have P and N. One side is P, other side is N. But when you talk about transistor, we have three terminals. There will be three terminals. All right, there will be three terminals. One is known as emitter. The second one is base. Third one is collector. So the transistor can be PNP or NPN. But as per NCRT, we have to deal with only NPN transistor. We have to deal with only NPN transistor beta. Alright. So what happens is, between two P, N will be sandwiched, or between two N, P will be sandwiched. So we have to study this. So we will be having something like this. This is N, this is P, this is N. So this is the arrangement which we have to study. N, P, N, and there will be three terminals beta. There will be three terminals. In PN junction we have two terminals, and in transistor we have three terminals. How many terminals beta? Three terminals. Right? Great. So application of transistor and logic gates. These are the two things which will be discussed in detail in the next video. Alright. So I hope that all of you are able to understand the basics which are required, and then we will discuss all the things in the next video. Alright. So thank you so much. Have a good day everyone.